derivative of natural log. Now, if you were to try, okay, if you were to try right now to rewrite this, then the first thing you would do, if we try and follow this pattern, is you would add 1 to that, right? You would add 1 to that, and if you add 1 to that, what would you get? X to the 0? But wait a minute, x to the 0 is 1, so 1? Wait a minute, derivative of 1 is not 1 over x. Something's wrong here, right? So it didn't work in this case. This is really the only case it doesn't work. And so you just have to recognize that this is going to be the natural log of x, what? Plus c. Let's do another one. What if I tell you that the derivative of something is 1 over 1 plus x squared? Yep. Arctangent, very good. This is arctangent of x plus c. You only are going to know that if you recognize it. And the only way you're going to recognize it is if when you were taught the derivative of the inverse trig functions, you were paying attention to those ones that were very common. This is one of the ones I told you was going to come up again. Okay, it will be an important antiderivative in Cal 2. All right. Let's get some language established here. The way I've started this out is I've always written down f prime, right? F prime is this, and I've asked you to find f, right? That's just because we know what f prime means. But now I'm going to write something else down. It's going to be just different notation and language. Definition. Capital F of x is called the antiderivative, or let's say an antiderivative of little f of x if the derivative of capital F of x equals little f of x. So let's go back to this example right here, all right? If I take this f prime out and change this to capital F, then capital F is an antiderivative of little f, isn't it? Because the derivative of this is this. So if I take derivative of this, I should get back this function right here. All this is a different notation. Instead of me writing down f prime and asking you for little f, from here on out, I'm going to write down f and ask you for capital F, which is its antiderivative. Think of it this way. This is a terrible analogy. I always think of capital numbers as being like the adult numbers, and then the lowercase are like the little kid numbers, you know? So it's kind of like these. This is like the capital, the parent function. When you derive it, you get its little baby function, which is you understand? That makes sense? I mean, that's the way I look at it. Capital F as being the parent coming down, taking the derivative, you get the little function, little f. All right. Now, I mean, it just really comes down to find the general antiderivative of I want to know what capital F is. You take the derivative of this capital of F and you get that. What's the capital F? Well, think about this. How many terms do we have here? We have 4 terms, right? When you derive something and you have 4 terms, you can do it term by term, right? Antiderivative is the same way. You can take the antiderivative of each term separately. All right? That's good news. So what is the antiderivative of 3x? So you know it's going to be an x squared, right?
3 over 2x squared?
So 3 over 2x squared is the correct answer. So capital F of x is 3 over 2x squared. Good. This might take some time for you to become quick with this, all right? But does everyone understand what you would have to do? Add 1 to the power, get the numbers to work out, right?
So plus 4 sin x.
Careful on that. Negative 4 is going to come for the ride, isn't it? Now you're not asking yourself what the derivative of cosine x is here. You're saying the derivative of what is cosine? Just sine, right? Just sine, not negative sine. So the antiderivative of cosine is just sine. So minus 4 sine x. This is just going to be plus 7x. Good. Because when you take the derivative of something in front of x, it's just that number in front, right? So this is the number that was left after I took the derivative of this. All right, and then this one. Okay, minus tangent x plus c. Now some Cal 2 instructors will actually count the entire problem wrong if you forget c.
Are you one of them?
I don't count it all wrong, but I do take off if you forget the c. I'll take off a point or something. I won't do nothing about it. This makes sense? All right. What are we doing? Good. All right. I need a better way of asking you to find the general antiderivative. Like I would hate to have to write down each time, find the general antiderivative, find the general antiderivative, find capital F of, okay, so maybe we'll have some notation for it. Just like when we wanted to do derivative, we had notation for it, like the prime. So there's got to be some notation we can use to let people know that we want them to find the antiderivative. So here it is. Notation. If capital F of x is antiderivative of little f of x, we write the following.
Tell me that's easier to write than
Right now, you're just going to have to, it's hard, well, there's a reason why that symbol is there, okay? It's actually, that symbol right here is called the integral sign.
So on Wolfram Alpha, when it says integral, that's the antiderivative.
Yep. That's called the integral sign. This function that we're trying to find the antiderivative of is called the integrand. Kind of like with a radical, the thing underneath was called the radicand. The thing inside of the integral here is called the integrand. This right here, this piece right here is called the differential. It's very important, the differential, But for right now, I want you to just understand that differential comes from the Leibniz notation. Remember how we like dy dx? This is just kind of right now keeping track of what is the independent variable. In the problem, the independent variable is x. So we are trying to find the antiderivative with respect to x. Just like when we took derivatives, we'd have to say with respect to what variable. Here it's clear what the variable is, dx. X is the variable. Got it? Now, the reason why that symbol exists, and I'm going to get ahead of myself here, I don't want to get too deep into this, is because that integral sign actually comes from the letter s. And just imagine it's been stretched out. If you stretch that s out, you're going to get something like that, right? S comes from, well, S is S is the first letter of the word sum, which you add things up, sum. And in Greek, it's the sigma, is the capital S. And what the integral and what the antiderivative actually wind up doing for us, all right, is this. Let's say you have a function, f. The derivative of it gives you the slope of the tangent line, right? The derivative of it. The antiderivative of it, believe it or not, will allow you to calculate the area below the curve. So if I draw a curve and I want to know the area below it, I need the antiderivative to do that. And imagine that you were going to try and find the area of that. The way that it's done is by approximating the area with a bunch of rectangles. So imagine I have these rectangles in here. You can tell me the area of a rectangle, right? That's easy. But the problem is if I approximate it with rectangles, I'm going to have a bunch of error, E-R-R-O-R, bunch of error, right? Because there's little gaps in here where the curve, I'm using straight lines and curves, it doesn't work. But the way I could get a better approximation is to use more rectangles, right? If I put 10 rectangles in there and found the area, that would be a decent approximation. If I put 100 rectangles, it would be even better, wouldn't it? Because they would get more narrow. I'd have less error. Yes? Yes? Okay. What would happen if I put an infinite number of rectangles in there? That's exactly what we do. It's a limit. We do a limit. So again, what happens is we take the limit as the number of rectangles goes to infinity. And that will give you the true area. So what happens is this sum, we involve a limit into this sum. The sum here comes from the idea that I'm going to add up a bunch of rectangles. I do a limit of this sum, meaning I let the number of rectangles go to infinity, and when I do that, I represent that limit of that sum with this symbol. And somehow later on, I'm not going to do it today, we will actually be able to find areas under curves very easily as long as we can find the antiderivative. Got it? Is that acceptable for you as far as why that symbol's there? It comes from the sigma notation, which comes from this idea. No. Taylor series, something completely different. Taylor series is the way that if you just hand me a function right now, like the cosine curve, right? Just hand me cosine x right now, right? Well, we'll do sine x. If you type into your calculator right now sine of 2, what is your calculator doing? It doesn't know what the sine function is. What it's doing is actually approximating the sine function using polynomials. And the Taylor series is the actual infinite polynomial that represents sine. So it's very different. That's Cal 2. You just got to wait for that. But while we're talking about the area under a curve, this is kind of like leading you into a little bit of what Cal 2 is about. You're going to spend a lot of time in the beginning of Cal 2 finding antiderivatives. All right? And as you might expect, it's going to get hard because think about when you took derivatives and it involved like quotient rule, chain rule, product rule. You remember how ugly the derivatives were. Imagine how difficult it's going to be to go backwards from that, to undo that. So what you'll do is there are going to be techniques that we use for finding antiderivatives. There's called, and by the way, you know how we called taking derivatives differentiation? The process of finding antiderivatives is called integration. And it's in the notes, and I'll put it on the board next time. So when it comes to integration, this backwards process, there are some standard tactics that we use. The first is called basic U substitution. All right, I'm going to show you U substitution. I'm going to show that to you a little bit today and maybe next week for sure. And then after that, you get to the other techniques of integration, which are called integration by parts. There is trigonometric integration. There's trig substitution, and there's partial fraction decomposition, which is something you did in pre-cal. And the reason you did it was for Cal 2. And so these techniques, you're just gonna get beat down with these techniques of integration. Then after you're done with that, the idea is that, hey, now you can find antiderivatives. So now you go and you say, all right, let's say you have a function, and let's say you have another function like this, and you can see where they hit each other, right? What's the area between those two? What's the area between those? So you can figure that out, right? Then you ask another question. Imagine taking this graph, the whole thing, and pulling it off the page so that it's out in three-dimensional space now. And take this curve, these two curves, this region right here, and wrap it around the x-axis and come all the way back to where you were. Okay? That would make a three-dimensional solid shape, wouldn't it? Yes or no? Maybe it'll be easier if I use an easier shape. Let's say we have this function and this function, and we look at that area and we wrap that around the x-axis. What would that create? There's that shape, right? There's that piece right there. If I wrap it around the x-axis, I'm going to create this solid block, right? Not solid, it's three-dimensional solid. I can put my hand through the middle of it, right? It's almost like a washer, really thick washer. Agreed? Yeah? What's the volume of that? We will answer that question. Yes?
So you're moving the entire shape?
The entire thing.
Not swinging around
I'm taking this entire shape, okay? Let's just say this is it right here. And I'm wrapping it around the x-axis. As I'm tracing through three-dimensional space, I'm leaving solid behind me, okay? So it's like tracing it out. And when I do that, it's going to create that solid. You see it? What's the volume of that solid? Well, why would that be useful? I don't know. Because if I took this, let's look at this problem in two different ways. What if I took that first quadrant of the circle? In Cal 2, we can find the area underneath that. And if I just let this be an arbitrary radius, I can actually come up with the formula for the area of a circle. If I wrap that around the x-axis, what happens if I wrap that around the x-axis? What do I get? You get half of a sphere. And I'm going to be able to find a formula for the volume of that, which is where 4/3 pi r cubed comes from. You can actually prove that formula in Cal 2, like where that actually comes from. With me? And then you can do things like, all right, well, great, what's the surface area of this? So we do that. And then another problem, which doesn't seem as hard, but actually turns out to be hard, is that let's say we have some curve like that. And I take this curve and I take this off the page. So let me see if I can do this. I don't think my battery's working there. And my camera, I can't unplug it, but let's say we take this curve, right? Here's this curve. Let's go from here to here, okay? Right there. If I take that curve off the page and I straighten it out, how long was it? That's called arc length. So what's the length of this arc? Understand? We can do that. All right, so those are just some of the things that you do. And then you can do like center of mass and moments of inertia, and there's lots of things we can do in Cal 2. That's just the beginning, but that's a little intro there. I want to do more antiderivatives. The key to the antiderivatives is pattern recognition. The better you are at derivatives, the easier Cal 2 is going to be. So let's try something, try and get you thinking about substitution. I just want you to think about it. You're going to have a lot of time to practice this. Let's start with this. Let me give you a function real quick. I'm going to give you what the answer is supposed to be. I'm actually going to start by telling you what the answer is. Let's say the answer is, yeah, let's do that. Let's say sine of x squared plus 1. There we go. Okay. Plus c. That's my answer. Take the derivative of that, everyone. What's the derivative of this? So chain rule, right?
Yeah.
It's cosine of x squared plus 1 times 2x. Agreed? Okay, now let's pretend that I just didn't put that on the board. Okay, let's just pretend I didn't do that. And now over here I ask you for the antiderivative of 2x cosine of x squared plus 1. And then I put this little dx here, like that. What is the answer supposed to be? Sine of x squared plus 1. Right? So the answer to this is sine of x squared plus 1. If I just look at this, that is a product between these two, right? When I do the antiderivative and try and take this back to where it came from, I am not going to do the antiderivative of this and the antiderivative of this separately. Because that's not even the way we took derivatives, right? You understand that that would be a no-go? What's the antiderivative of just 2x? Just x squared, right? And then the antiderivative of this, maybe you think it's sine of x squared plus 1? I don't know. But that's not that, is it? It's not what it's supposed to be? I guess all I'm trying to do right now is just to get you to think. By looking at that, can you see that that's the result of chain rule on that? Can you see that? When you look at that, can you say, yeah, the derivative of this is actually that, and that means it had to have come from that. It's kind of tough to see, huh?
So it kind of just cancels out then, like when you're finding the antiderivative?
It does. It kind of goes away, right?
Yeah. Because
Yeah.
since it comes out from the middle.
Yeah.
If it's chain rule.
Yeah. But do you see the inherent issues that we're going to have here?
Yeah.
There's going to be some problems. All right, so let me introduce you to the substitution. All right? Here's the integral that we're trying to figure out. We want to try and find the antiderivative. We know the answer should be this. So with this technique of substitution, what you do is you look at your integrand and you ask yourself a question. Do you see something? Do I see something and its derivative both in there? So do you see something and its derivative there?
Yeah.
What do you see?
X squared plus 1.
X squared plus 1. Its derivative is what? 2x, and it's right there. Right? So I see something and its derivative. So what I'm going to do is I'm going to make a substitution. My substitution is I'm going to let u, and u is just the standard letter that we use. I will let u be that something. Not the derivative of it, just the something. So x squared plus 1. What I'm going to attempt to do is rewrite the problem. We did this in college algebra when we had complicated quadratics and we did substitutions, try and make it look better, easier to work with. Same thing here. All right, so if u is x squared plus 1, just tell me if you believe the next step. If I write that equation down, do you believe that this is true? Du dx is equal to 2x. If I take the derivative of the left side with respect to x, I get du dx. Derivative of the right side with respect to x, I get just 2x. Yeah? Now, I would like for you to write this. Do you agree with that? I'm multiplying both sides by the differential dx. So almost like clearing a fraction. Yes? Okay, so all of this was just me on the side doing this thing called substitution. Let's go back to the original integral and let's rewrite it. I'm going to replace this right here with what?
Is it the 2x dx?
No, what's this right here? What's x squared plus 1? That's u, right? I'm going to replace that with u. And then, do you see the other part that I can replace? Do you see 2x dx? This dx is actually part of the integral. It's being multiplied. And this right here is the other part. So these two together are going to be replaced also with what though? What's the 2x dx going to be replaced with? Du. Understand? This is going to be replaced with u, and those two parts are going to be replaced with dx, or du. Are y'all following me? Okay, let's rewrite this integral. It's integral, what? Du, and you could put the du first, that's fine. I'm going to do that because you said it. Du, and then what else? Cosine. Times cosine. The cosine didn't go anywhere, right? Cosine of u. All right, cosine u. And that's the only thing there now, right? I'm going to rewrite this as integral cosine u du. What I've done is I've changed the variable from x to u. And that's a much cleaner integral, because what this is really asking you is, what's the antiderivative of cosine of u? What's the antiderivative of cosine of u? Sine of u, right? So the derivative of what is cosine u? Sine u. Yes? Do you all agree with that? So if I were just asking you to answer this question right here, you would say that this must be sine of u plus a constant. People always ask me, like, what happened to this integral sign and what happened to the du? Remember what this is asking. It's, all this notation means is tell me the antiderivative of that. What's the antiderivative of this? That, right? Plus a constant. So your answer to this question of what was the antiderivative of this, your answer is sine of u plus c. What the hell's u? Well, what was u? X squared plus 1. So I can rewrite this as sine of x squared plus 1 plus c. And that's what we said it was going to be, right? That has some inherent issues in it, doesn't it? I mean, this is... Let's do another one, since this, y'all look like you're really enjoying this. This one really had my other class upset, this next one. You may not do the top and bottom separately. No go. That would be like you taking a derivative without doing quotient rule. You can't do antiderivatives that way either. Could you split this up into two fractions and just figure out like something over x? Like, can you do it two fractions there? No. If it was flipped over, could you? Yes. Okay, so side note, keep that problem up there, we're going to do it. But if this were flipped over, what I would do is I would do 1 over 3x squared plus x to the 6 over 3x squared dx. This one right here, I'd convert each of those into x to a powers. Right? This would be 1/3 x to the negative 2. This one would be 1/3 x to the 4th. And then I could use the same thing we did earlier. You think you could do that? Yes? This I can't do that with though. Can't split it apart. My hint to you is that you can use substitution. You've got to see something and its derivative. I'm just going to have a seat until somebody sees it.
Is that a function times the derivative?
Pardon?
Is that a function times the derivative?
How do you mean?
Like because of the dx?
No, don't worry about the dx right now. Just forget the dx. Like,
Well, the bottom is essentially squared, right? So,
what's squared?
Well, the 1 plus x, because when you do quotient rule, you know, the bottom part of the fraction is something squared. So could you factor out?
I wouldn't try and look at this, like in your mind right now, I wouldn't be trying to say, like, that's the quotient rule of something. I wouldn't, that's going to be really difficult if you approach it that way. I think what you should be doing is thinking, do I see something and its derivative in this problem? Is there something in there that I can isolate that when I take the derivative of it, it's also in this problem? It appears somewhere. What do you see? Did you say yes?
Yes.
Okay, what do you see?
Maybe arctangent of x cubed.
Okay, okay, so you're way ahead of where. You see arctangent of x cubed?
Because if you do x squared, you're getting it's x cubed.
That's the correct answer. That's actually the full answer plus c. So how did you get that?
Well, because but I was taking what he said, 1 plus x squared at the bottom is arctangent, but x squared, if you take the power of that one, you would get x cubed squared is x to 6, right?
Mm-hmm. I can't teach that. Okay? This is the truth. This is what makes Cal 2 hard. It's intuition. There's an intuition here. And it's very demoralizing when you can't, you keep beating this thing over the head and you can't see it. We try and give you as many methods and steps and procedures as possible, but at the end of the day, you have a familiarity with arctangent that makes you comfortable enough to see that. If you had no idea about the arctangent derivative and how it worked, it'd make it much harder to see that. So, yeah, again, I don't know how. I wish I had a magic pill or something, but I don't. Sticking with the theme of trying to see something in its derivative. How about that? So the thing that would have tipped me off here is I see 3x squared. What's the antiderivative of 3x squared? What's the antiderivative of that? X cubed, right? X cubed. Is there an x cubed in here? Not quite, but if I rewrite it like this, it's there, right? Y'all see that? So if I rewrite this, x cubed squared is x to the 6th. Now I see something and its derivative, right? Something in its derivative. So I'm going to make a substitution. I'm going to let u be what? X cubed. And then I'm going to say du dx is 3x squared. I want to put a little disclaimer here. When I was in Cal 2, I was not the student who could see it. All right? I had to work hard to get to the point where I could see it. So I'm not trying to demoralize people here and be like, look, if you didn't see that, you're dead in Cal 2. But you cannot expect it to be like Cal 1 where, hey, product rule, once you understand the rule, it's just a rule. Cal 2 is different. You have to be able to see patterns and recognize things, and the only way you do it well is to keep trying and trying and trying. In fact, I went back a few years ago and I pulled out all my Cal 2 notes, and I tried, it was the first semester I ever tried to do every problem in the book, like all the homework problems, well, more than the homework problems. I tried to do every problem I could. And I got about half of them wrong, easily, half of them wrong. But I kept trying. And so that's what you need to do. You need to just keep the effort. The effort level in Cal 2 goes up a lot more than in here. All right, so there, right? I'm going to put du 3x squared dx, like this. This is the standard thing I'm going to do every time I do a substitution. And now what I'm going to do is go play this game where I go try and basically rewrite this entire integral. So I'm going to replace this x cubed with what? X cubed is u, right? And I'm going to replace, let's see, I'm looking for this. I'm looking for 3x squared dx. Do I have it?
Yeah.
I have 3x squared dx. It's this whole thing right here. And remember, that dx is really on the top, okay? Because this is like dx over 1. It's like a fraction, so it's really up top. So how could I rewrite this integral? Du, right? This is du over what? 1 plus u squared, which is the same as 1 over 1 plus u squared du. So what I'm doing is I'm dropping that du back out on the outside. And that's what? Arctangent of u. That's arctan u. Plus c. So you have to recognize that. We did that earlier, right? But with x's. So this is arctangent of u. But what was u? X cubed. So this should be arctangent of x cubed plus c. And the good news, if there's any good news, is that you can always check your answer, right? The derivative of this would be 1 over 1 plus this squared, which will give you the 1 over 1 plus x to the 6th, times the derivative of what's inside, which is 3x squared. I've got a few minutes. I want to see, I'm going to just do one quick little change to this problem here. What if that 3 wasn't there? Now that may look like, okay, complete disaster now, but it's actually not, okay? So remember how I said you want to look for something in its derivative? It's okay if you're off by a constant. It's okay if you're off by a constant. So when I look at this and I kind of reevaluate it, I would have this, right? I could rewrite the problem like that still. And if I come over here, I could write u is x cubed, du is 3x squared, or sorry, du dx is 3x squared. I could write this, right? Now I'm trying to get this to match up. So I'm saying, all right, 3x squared dx, I can replace that with du, right? But I don't have 3x squared dx. I have just, what? X squared dx? So take this little equation right here and divide both sides by 3. Or scale by 1/3. So what if I put 1/3 du equals x squared dx? Do you agree that that's still the same thing? So now what I'm going to do is I'm going to replace x squared dx with what? 1/3 du instead of just du. So my new integral over here would become 1/3 du. Right, that's 1/3 du. This is 1 plus u squared. And then what would happen here? 1/3 here? That 1/3 is a constant, isn't it? Constants always just come along for the ride, whether or not you're taking derivative or antiderivative. If they're attached to a function, they come along for the ride. So what I would do is I would actually pull this 1/3 out in front, like that, and then I'd put a 1/3 out here like this. So I put a 1/3 out here. And you can check for yourself. If you take the derivative of this, right, you're going to get 3x squared over 1 plus x to the 6th. That's what you would get if you do that. Then if you multiply that by 1/3, that 1/3 kills off that 3 on top, and you get your x squared. So it's okay to be off by a constant. All right, what is your homework? You have food, turkey to eat, yes, that's true. What else do you have? Optimization homework. Make sure you look at that. We're going to have a quiz on optimization. I'm not going to assign any of the antiderivative homework yet. Just make sure you're caught up on your optimization so that when we come in on Monday, you'll turn in. No, the take home from last time. That's due today, or Monday. You want it Monday?
Monday, because people are here. What if we have it today?
If you have it today, I'll give you a bonus for turning it in early. or today on time. If you need more time on the problem from last class, remember the problem from the, it was an optimization problem that we did with the parabola and the point, and I said find the minimum distance.
Looks like you just wanted back the derivative.
Oh yeah, I just wanted the derivative set equal to 0 and solved using either a computer or something, and I said I'd give bonus if you did it with Newton's method. If you have that ready for me today, I'll take it, I'll count points. If not, have that ready on Monday. Everyone have a good weekend.
So do we have to